Let us now discuss a more generalized definition of a gradient of a scalar field. We shall discuss the gradient in 2D and 3D setting. Um, we will compare this definition, this generalized definition, with the definition of a single variable differential or differentiation of a function with respect to x. In the case of single variable calculus, if we have a function f of x, we want to find out the gradient or the differential of that function with respect to x, we can employ the definition of flux over boundary. So we say that within the step delta x, we find out the flux at x plus delta x, and then add that to the flux at x. This is similar to saying that we have got a function value at f of x plus delta x. We subtract that from value f of x at x, and then divide the whole by the step size delta x. So in the case of flux definition of the differentiation of function with respect to x, we have the function value at x plus delta x. We multiply that with the normal, and this normal is corresponding to the step delta x. So together, this gives us the value of flux over the boundary delta x. Then we add the value of the function at location x. This is the same location where we started, and multiply that with the normal in the opposite direction. So this second term is actually the flux over the boundary and is facing opposite to the value of the flux at the right hand boundary. Now let's see whether we will follow the same logic in the case of generalized definition of a gradient of a scalar field. So in the case of gradient of a 2D scalar field, we take a 2D body, and within that body we take a small element. So previously in a single variable calculus we had a small length delta x. In here we take a small area, and we find the function at that point over the boundary ds on this function. So we have the boundary of this small element as ds. F times ds will give us the function value at this ds, and then we multiply that with the unit normal vector to get our flux. After that, we integrate that all around this purple body. So that gives us the flux over this area. The reason we are taking a small portion of this area initially is that we have a 2D setting, and in 2D setting, we normally are dealing with surfaces. So this is similar to the previous case of single variable where we were dealing with just simple steps, which was of size delta x. In the case of 2D setting, we are dealing with curves or surfaces, and correspondingly in the 3D, we will be dealing with areas then. So we are going one step up as we move from the single variable gradient definition to the multi-variable gradient definition. Now, this boundary will be corresponding to this whole area, so we need to divide that by the area B, area of this B, as we did previously, where we divided the whole function by the step size delta x, and then we make this area tend to 0. A similar logic can be applied in the case of 3D setting, where we have got again a function. We this time we are taking a small volume, and we multiply the function with the surface area of this volume or this box, and then multiply that with the unit normal vector, integrate it about the whole area. And this gives us the volume because we have integrated our f time n about the whole box. So we need to divide that by the volume, and after that we take a limit and make the volume tend to 0. So as we can see, there is a clear analogy between the 2D and 3D setting and the single variable definition of differentiation. Now, one last thing, this definition of gradient will give us a vector quantity. As we can see, f is scalar. It gets multiplied with a vector, and we get ultimately a vector quantity. Same is true in the case of 3D setting. Let us now derive the equation of gradient of a scalar field. So the volume of this box, that is delta x1 times delta x2 times delta x3. So that volume, what we are actually trying to do is we will plug the values in this definition. So the volume in this definition is delta x1, delta x2, delta x3. Then we have this integrand which need to be defined. This integrand is having the value of the function times the normal of the function times dA. So let us try to find this integrand. If we assume this cube, it has got three sets of areas. So two areas are in E1 direction, two areas are in E2 direction, and two areas are in E3 direction. So we will try to find out the flux, which is the value of the function times the normal vector corresponding to E1, E2, and E3. And that's what we have done. The flux is equal to f of x plus delta xi ei dA. So this is the value of the function when we take a single step in the ei direction. Ei can be the ith direction, it can be E1, E2, E3. So the value of the function corresponding to the step which we have taken. And that is multiplied by the normal, which is ei, and the area dA. Please note that this is similar to what we had in the single variable setting where we had a vector at t plus dt, t plus delta t, and that was getting multiplied with the normal vector. So that's why we have the function value. We are moving, we are taking the step in eith direction, or this ei can be either e1, e2, e3, and then we multiply that with the normal vector and times dA, which is the area of this cross section. Similarly, we add that with the function which is f of x. Now this is the previous step function. Multiply that with minus ei into dA. So this is the step where we started from. That step has to be multiplied with the negative of the normal vector, and then this flux have to be multiplied with dA. So this second term is analogous to our single variable calculus, as that is the step where we started from, and that is multiplied with the normal vector, which is in the negative direction. If we write summation I is equal to 1 to 3 with these two terms, that means that we are taking the E1 direction, E2, and E3 directions. Now we can take f of x plus delta xi minus f of x as common, and we get ei ai getting multiplied with both of these terms. And we can define f bar as 1 over ai times FDA integral. Now what we have done is, in this equation, we have multiplied and divided our whole equation by AI, which is the area of the cross section. So we multiply and divide this whole function by AI. The AI which is divided, that is combined with our function f, and times integral dA. So we write this in a bit simplified form of 1 over AI integral f dA. This is, please note, we call that f over bar. So f over bar x plus delta xi ei minus f over bar x. Now the volume can be defined as a1 delta x1 or a2 delta x2 or a3 delta x3. So what we are saying is we have got a1, this face we call a1, and that can be multiplied with this delta x1. This face we call a2. It can be multiplied with delta x2, or this face we call a3, the back and front face. We multiply that with delta x3 in order to get our volume. We divide this whole integral as per this definition by volume, so which is ai delta xi. We can write this 1, 2, 3 in the form, in the ith form. Once this is written like that, we can cancel out the ai with the ei. So, and if we take the limit, the delta xi tends to 0. We have made xi tends to 0 because a we assume as a constant. So based on that, we make, instead of volume tends to 0, volume is made up of axi, and xi is that step which is changing. That's why in limit we have to make xi tends to 0. We get curly f by curly xi ei. And that is the definition of gradient which we described earlier. So in a similar way, we can work out the definition for 2D setting using the same procedure. The main idea behind explaining the 2D and 3D setting is that we want to show that this equation which we get, that is actually derived from the same stencil which we are using in our vector calculus. So we are using this definition throughout our vector calculus, and we will be trying to derive different definitions based on this one. So based on this single variable calculus, we worked out the flux definition. Then from the flux definition, we worked out gradient of scalar field for in 2D and 3D setting. Now let us see what is a vector field. A vector field is a key concept in vector calculus, and it has got great application in advanced structure mechanics. It is a function that assigns a vector to each point in space in a mathematical language called in manifold. So we have got a space, a 3D space, and we assume that the whole space is full of vectors. Every vector has got a magnitude and a direction, and that vector is giving us information about certain vector quantity. A vector field tells us how the vector is changing within a particular field. Like, for example, we have got a gravitational field. In the case of gravitational field, we assume that there is acceleration due to gravity in on Earth, which is 9.8 meter per second square. So if we want to draw a vector space corresponding to the gravitational field, we can say that the whole space is made up of vectors which are like this, and every vector within the gravitational space is telling us the acceleration due to gravity, which is a is equal to 9.8 meter per second square. All the vectors are of same size because acceleration due to gravity on the earth stay the same. In most of the places, acceleration due to gravity is constant, and we will have set of arrows within this space, everyone facing down, and all the vectors having same magnitude. Now we can study the effect of movement of a body within this gravitational field. So this is our E1, E2, and E3 space. Now let us discuss the vector field describing a gradient of a surface. Imagine we have got this red surface. The equation of this surface would be f of x1, x2 equal to constant. We draw it in a 3D Cartesian system. Now we want to find the vector field corresponding to this space, corresponding to this surface. So we can work out the gradient of this surface using the equation which we discussed above, the gradient of a scalar function equation. So please notice that gradient of a scalar function is a vector. So why? Because we are multiplying the unit vectors with it. So this gives us a vector. Now, using this equation, we can find out the gradient of this surface at different locations, and we would get lots of arrows. Each arrow at a particular location will tell us the gradient of this surface. Now, if we are interested in finding out the maximum value of this function as we move along the function, so we can find that out using the gradient vector field. We can see that the arrows at the origin are 0, and as they move out of origin, their magnitude slightly increases. So this tells us that the function is becoming maximum as we go away from the origin. And that is true from this graph, that the value of the function increases as we come out from the minimum value of the function. This also tells us that the value is maximum at the edges. So value of the function is maximum at the edge. One important thing to appreciate in the case of gradient of vectors is that gradient of vector is always normal to the surface. However, the single variable differential equation is tangent of the surface. The reason the gradient is normal to the surface of the function is that we are actually trying to find the rate of change of the function, and then we divide that by a constant area or the constant volume. In the case of 1D setting, we find the difference between the functions, and that difference is then divided by the step size in order to get the orientation of the tangent. In 2D and 3D setting, the orientation is not obtained by simply dividing the function difference by areas or volumes. In a similar way, we can have another function which is shown over here, and this function is distributed among 4 quadrants, and every quadrant has got its own gradient. So again, this is the slope of the steepest descent, or which we have found, or the gradient of the function at each and every point. Gradient is again is the normal to the surface of the function. This sort of field tells us where the valleys and peaks are, and which place the function is becoming maximum or minimum. In a 3D setting, we will have a function looking like this one. We already discussed the 3D space of a gravitational field. This brings us to the definition of gradient of a vector field. We have discussed gradient of a scalar field. Then we discussed gradient of a scalar field in 2D and 3D setting. Now we move to gradient of a vector field. The definition of gradient of a vector field is shown over here. So again, this is the same equation which we wrote in the case of gradient of a scalar field. So the same type of equation. In the case of gradient of scalar field, we had to take the dot product of the function with respect to its normal vector. In the case of gradient of a vector field, we take a vector and take a tensor product with the normal vector. So what do we mean by that? Let us check the trend first. So we start from a scalar field. scalar field has got magnitude, it has got no direction. When we take its gradient, we get a vector quantity using the definition of gradient of a scalar. Now, if we take gradient of a vector, so we should get a tensor quantity. So we are going one level up from a scalar quantity, we go to a vector quantity, and then from vector quantity, we are going to the tensor quantity. That's why I have written it as a vector and another product which is having a cross and a circle. This is tensor product. And tensor product is telling us that if we take a vector and take a tensor product with another vector, we get a tensor quantity. So the example of this would be that we have a body which has got supports and that is subject to some loading. We imagine that this body is divided into infinite spheres. Every sphere has got infinite vectors radiating out of its center. So the spheres are made up of vectors in all the direction. These vectors can be displacements, they can be forces, or they can be any other quantity. But these are vectors which are in 3D setting. Previously, we had a scalar quantity, so this whole body at every point had got a scalar. Then we said that there is a vector field. So this whole body had vectors at every point. So the gradient of a vector field is telling us that how this particular sphere having bunch of vectors will change as we move from one step to another step. So this bunch of vectors might be changed into ellipsoid of vectors. I've shown just few vectors over here, but this ellipsoid is also full of all the vectors which were over here. So please notice the analogy between the single variable calculus, multivariable calculus, and then the whole tensor calculus. In the case of gradient of a single variable calculus, we move from value x to value x plus delta x and try to find out what the change in function would be. In the case of gradient of a 2D scalar field, we moved from one point to another point and tried to find what the change in the scalar would be. The similar argument applied in the 3D setting of the scalar field. Gradient was just movement from one point to another point within 3D space and trying to find out what the change in the function would be. Now, in the case of vector calculus, we have instead of scalars in the scalar field, we have vectors, bunch of vectors, and we are moving from one point to another point within a body, and we are trying to find out what will be the change in all the vectors when we take this step size. Please note, in the case of gradient of a vector field and gradient of a 3D scalar field, we are trying to find out the rate of change in all the possible directions.